All right, so in Studio 5, we are going to be working with decoders, encoders, and we'll also try to synthesize a logic function using a standard 3 to 8 decoder. So that I've broken this studio down in 3 tasks. Uh, Individually, these are supposed to be very straightforward and not that time consuming. Um, so overall, it should still be doable in 1 week. Let's see how this goes. So task 1 is about designing the standard 74x138 decoder chip. The inputs are active high. One of the enables, G1, is active high. G2A and G2B are enables that are active low. You have all the 8 outputs that are active low. So this 74x138 chip, we studied this in a previous lecture, that was the 3 to 8 decoder. And if you refer back to your notes, you should be able to take a look at this, which is essentially what goes inside that chip. The goal with task 1 is to do a behavioral model. So it's supposed to be simple, it's supposed to be using uh, what we call the signal assignment statements, right? So it's a behavioral model. So in one VHDL code, you should be able to wrap it up. You are essentially going to have in your entity, what do you have? In your entity, you can define a 3-bit input here, 3-bit enable here, and an 8-bit output here. And depending on your choice, you can treat them as individual bits or you can treat them as vectors. uh, I leave that choice to you. So you can use that, you can define them as logic vector, right? Standard logic vector, or simply standard logic, um, depending on what you feel more comfortable with. So that's a design choice that you are making. And you also have this truth table handy for you to be able to write those signal assignment statements. Um, let's see, did I write a note here? Yes. So since I have 8 outputs, I will just show you guys maybe an example of how to write an expression for y0, right? So if you observe y0, y0 is active 0 only when you have things that are enabled and you have a 000 in your input code, right? And this blue highlight over here maps to that output right there, right? And as you can see, it is a simple AND gate between those inputs and the enables. So let's try to write a expression, a logic expression for y0. So what I'll do is this, right? So I'll say y0 signal assignment operator followed by I need G1. So I can say G1 and not G2A and not G2B, right? So that takes care of the enable checking, and you can AND that with X not X0 and not X1 and not X2 semicolon. So Y0 will be a 1 in this case, right? So all of this needs to get knotted. So I should put a knot around all of this. Not, right? So that would be an equation for Y0, and in this case Y0 is an active low output. Similarly, you can write expressions for y1, y2, y3, so on up to y7, write them into your VHDL file. Um, it and as I said, it depends on your choice whether you treat them as individual bits or as a vector. Completely up to you. Um, but that's it. That will complete task one. The if you use select x when those when select when statements, you are absolutely okay. LED is active high, so what would happen is when you connect these outputs to LEDs, all of them will light up and only one of them will be off depending on the input sequence. You are right, LED is active high, but the outputs of the 74X138 chip are active low. So what this means is these cases, the first three cases, all the LEDs will be on. And then depending on the input choice of x1, x0, x1, and x2, one of the LEDs might be off. So, you know, that's why we have the not over there. Yes, Alex says when else statements are fine. Select when, depending on the your comfort level with the VHDL statements. You can choose whatever you want. I'm just showing you one way to do it. You will have multiple statements. You will have 8 such statements. Then you will do the same thing, right? You will generate the bit stream, download it onto the board, and then demonstrate your implementation to Lauren. And you can just use a couple of input cases with the enable and without the enable to demonstrate your work for task 1. Next, if I go down this list, I have task 2, which essentially needs task 1. So in task 1, we designed a 74x138. In task 2, we do a structural model. Where did I write that? So we need a structural model for task 2. But in this structural model, you only have two pieces. One is the result from part A, and then depending on how you convert this particular statement into its corresponding canonical sum of products form, you will have certain connections between the 74x138 to the NAND gate. Only one NAND gate is necessary for this. Now, for this particular task, I would refer you back to this example that we did during the lecture, right here. So when we had to implement this particular function here, which was already in canonical sum of products form, we just took the minterms 2, 4, 7, and we connected those particular ones. Sorry, we connected the max terms for this through a NAND gate to get the output out. So we needed 7, 1, and 2. 7 was here, 1 was here, and 2 was there. We connected those max terms to a NAND gate and done. So component 1 is from task 1, and you would have to just add up a NAND gate in front of it, make those connections. So you would, when you're writing the structural model, you again have to use the same 3 steps, right? Component declaration, component instantiation, signal declaration. So you can do task 2 that way. Please refer to this example. Depending on which minterms you have, it'll just be connecting those guys to the NAND gate. Over here in task 1, you are asked to use slight switches for all the inputs and enables, and you can use LEDs for the outputs. For task 2, you are asked to use slide switches again for the inputs as well as enables. And because you have only one output here, F, for the function, you can just use one LED. Also note that there will be outputs of the decoder that will not be connected to anything. So you can just connect them to some LEDs of your choice, or you can force them to be zero. It's up to you what you do with those outputs. Generate bitstream, download FPGA, demonstrate the implementation to TA. That is standard. After that, task 3 is about an 8 to 3 priority encoder. And whenever we talk about combinational design, what do we say? We say, give me the truth table, I will tell you everything there is to know about it. And guess what? We have a truth table right here. In fact, in lecture, we wrote down expressions for the outputs. And you may choose to go back and look at those expressions, or you might just be able to derive them over here, right? So for what is the expression for a2 underscore l, a1 underscore l, and so on. What we did earlier in our lecture discussion was, we for the priority encoder, first we came up with row expressions. So for each row in the table, we wrote an expression out. We defined them as h sub 0, h sub 1, h sub, you will go all the way to 7 in this case, 0 to 7. And then y0 will be row 1 plus row 3, y1 will be row 2 plus row 3, and so on. This was the 4 to 2 priority encoder. And I think we did, I think right here. Yeah. So this is the 8 to 3 priority encoder and all its expressions. Do we have to use active low input uh, for task 3? Well, just take a look at this. All the inputs are active low and enable is active low. All inputs and outputs are active low. So yes, all uh, that's exactly how you are supposed to do this. So the idea is to replicate the standard chips. And once you have the expressions from lecture, right here, uh, now, let me ask another question first. The row expressions were sort of the intermediate expressions, right? That was not the input, that was not the final output. So what are we going to use? Well, we are going to use signals in this case, right? So we are going to define signals, which can also be used for behavioral designs. They not only apply to modular designs, they also apply to behavioral design, and their use is very similar. They are outputs that are not the final outputs, and as you can see, those row expressions are just that. So I can have those 8 expressions. You can say signal h0 comma h1 comma h2 and so on. Those will all be standard logic, and before you actually do the begin and end, you have to define the signals and then use them in your uh, architecture, just the way you did with signals in the top level. You can also use signals for behavioral models. Task 3 is a behavioral model. If you have so the expressions are noted down over here, but you could derive those expressions based on the truth table here as well. How do we handle the enable and GS and EO? All right. So enable, there is only one enable, right? Active low. How do you handle that? Well, connect it to a switch, and only when the switch is low, the output should be available, right? So whatever expression you have for, say, a2 underscore l, it should be enable, not of enable, right? And whatever is next, right? So enable has to be low, followed by whatever remaining expression you have for a2 underscore l. This can be viewed here as well. I think that's it, right? So that's the same truth table as before. All right, let's leave it here. Let's go back. How do we handle enable? With a switch, and in the expression, you would do this. Not enable, and then followed by other things. GS, got something. Got something is active when you have any one of the inputs as active. So you are going to use the OR operator, right? And you might have to use not of this or this or this or this or this. You know, if you guys have, if you guys are struggling with the active low versus active high, here is a quick adjustment. Implement everything with active high, and then at the end put not in front of things, and you are done. Yeah, right. So that's what I'm saying. Try to, so once you, if the active low, logic low is confusing, do it with this first, right? Once you do it with this, all you have to do is put a not in front, right? And you will get your the corresponding active low outputs. Let's see. Kevin says, do we have to do all of these tasks within one? No, no, no. So Kevin, you can. I would recommend doing this. I would recommend you trying to finish task one, and then task two, and then task three. That just keeps you moving in terms of your design, right? So you can do it in the same project, but have three different design sources with probably three different XDC files. And then depending on which one you are trying to get checked off for, you can remove the design sources and the XDC file of one task and then bring in the other ones. All right, can you write a sample row? Yeah, that's exactly what it is, right? So A2 is not of H4 or H5 or H6 or H7. Yes, put not on output. How would I do that? Well, there is a add sources options, and there is a add design sources options, and there's also add constraints option. So for example, if you are working on task 1, you create a new design and a new constraints, work on that, and then when you are ready to move on to the next, you right click on those VHDL and XDC file and select remove from project, and then add new design sources for task 2, and so on. And when you go to check off, remove certain design sources and bring in the new ones for that task. So by right clicking on the VHDL file or the design file, you should be able to you can also disable them when checking others. That should also work. No, no, no. So the input doesn't become. I'm confused by the conversion. So here, try to do the outputs by assuming that everything is active high first. Once you are ready with active high, then you start working on active low. That's probably uh, the easiest way to tackle this. So if you want to have an active low output, you put a not in front of the logic expression. If you want to do an active low input, just exactly what we did here. You see this? How did we tackle an active low enable? We just did that, not G2A, not G2B, right? So because this is a very sort of a, it goes in a pattern, right? These expressions go in a pattern. Um, you can also do, and if you're struggling with that logic low versus logic high, do the active low, active high first, and those expressions are there in the note straight away. Then you can work on this active low part. All right. I'm going to stop the recording here, guys.